Hello, this is Yuchao Li. I'm going to present our work, Data-Driven Rollout for Deterministic Optimal Control. This is a joint work with three professors, Carl Johansson, Jonas Martensen, and Dimitri Bersikas. The problem we are interested in solving is deterministic, infinite horizon optimal control problems where the system state evolve according to stationary dynamics, while stage cost is accumulated along the trajectory. The stage cost is non-negative, and we allow value infinity to represent constraints imposed on states. The control constraints are explicitly given by constraint sets, while all the states belongs to the state space X. For a function that maps X to U, if all the control constraints are respected, we call it policy. Its cost function is defined as the sum of infinite sequence of stage cost accumulated along the trajectory under the influence of policy mu. The goal of this problem is to obtain the optimal policy mu star such that its cost function equals to the optimal cost defined as the optimal value of this expression minimized over the infinite sequence of controls subject to the control constraint and system dynamics. Except a few cases, this problem cannot be solved exactly, so various approximation scheme exists. Our approach belongs to the broad class of approach called approximation in value space. Its validity is rooted in Bellman's equation, which states the optimal value, optimal cost of current state equals to the stage cost plus optimal cost of next state minimized over all control. In addition, the optimal policy attain the minimizer of the same expression. Due to the curse of dimensionality, we cannot get J star. So in place of J star, if we use some function J bar and assume that J bar carries some information of J star, we may expect the policy we get mu tilde also be desirable in a certain sense. And this optimization step, we call it online play, for reasons that will be clear shortly. And in order to perform this step, we need to have this J bar beforehand. The process of obtaining this function J bar, we call it offline training. And rollout is a special case of approximation in value space where one uses the cost function of a base policy as J bar. A fundamental property that holds for rollout is called sequential improvement condition, which states in place of J star, if we use J mu, then the value of this expression is upper bounded by J mu, and it holds for a broad class of problems. Now let's introduce the background of our study to put in context our contribution. The related DP theory dates back to the 60s, and the fundamental property that we rely on called monotonicity, which states if we have two functions of states, one bounded by another, then we evaluate their value at next state, and we have this inequality due to assumption. By adding the same stage cost on both sides, we preserve the inequality. The second property is called fixed point equation, which states for all policy mu, we have this fixed point equation holds, which is really nothing but Bellman's equation by replacing the control constraint sets with singletons that only contains mu x. By combining monotonicity and fixed point equation, we get this upper bound property, which states for all policy, if we replace this J mu with some J tilde and get this inequality, then we know that J tilde is a universal upper bound of J mu. In terms of theory on computation, we know that when J bar is set to be equal to J mu, then the online play step is one step of Newton's method with starting point J mu for solving Bellman's equation. This has been known since 60s in various contexts. However, what has only been revealed recently is that even if there are approximations involved, similar interpretation of online play as one step of Newton's or Newton-like method holds true. And this has major implication because this means the cost function of J mu tilde we get by online play is much closer to J star compared to the distance between J bar and J star, due to the superlinear convergence of Newton's method. And this motivates our study on rollout and its related approaches. And for the related suboptimal scheme, we first mentioned rollout, which in its exact form is obtained by setting J bar equal to J mu. But we can also involve approximation, whereby instead of evaluating over infinite number of stages, we may evaluate only m stages of stage cost, after which use some additional J hat cost function to represent the tail portion of cost. Another aspect is, instead of optimizing only the current control, which we call one-step look-ahead, we may as well also optimize the subsequent L-1 controls, which we would call L-step look-ahead. And those two ideas are integrated seamlessly in Tezaura's TD gamma algorithm, introduced in the late 90s, which achieves superhuman performance in backgammon. Surprisingly, similar architecture are applied by both AlphaGo and AlphaZero, albeit there are some difference in some regards. So the look-ahead tree here represents the L-step look-ahead, which enumerates all the moves and counter moves in those two steps. At the leaves of this look-ahead tree, according to the base policy, the game is simulated along some number of stages, after which the terminal position is evaluated according to some cost function approximation. And both the base policy and the terminal cost approximation need to be obtained offline while the problem is solved online. The key theoretical concern here is to make sure that the rollout policy outperforms the base policy, which means its cost function is no more than the cost function of base policy. For another related scheme, of course, is model predictive control, MPC. Here is a typical formulation of MPC. And if we use the terminology of rollout, we see this is the terminal cost, and this is base policy, which would be the mode 2 prediction or control beyond the control horizon. And this is terminal constraint. And those ingredients need to be obtained offline while the problem is solved online. The key theoretical concern is the recursive feasibility of numerical solution and stability of the closed loop system, where typically one uses the optimal value J tilde as the Lyapunov function. It has close connections with both DP and rollout and has been known for a while. Now here comes our contribution. We know that exact rollout is obtained by setting J bar equal to J mu, and we have it outperform the base policy. However, in this case, we need to obtain the values of J mu for all x, or at least have means to compute them. What if we can only compute a subset of J mu, not all of them? Can we still get this outperformance property? Well, the answer is yes, but only for some type of S. And our key inspiration came from Rosalia and Brawley's paper in 2018, and the desired condition translates to the following property, which states if we have X belongs to the set S, we require its subsequent state under the policy mu also belongs to the set S. This forward invariance property would guarantee our desired behavior. And in detail, the effective J bar would be the sum of cost function plus an indicator function, and this ensures sequential improvement condition, which in turn guarantee the outperformance property. Since our analysis relies on fixed point equation, which put little restriction on the problem, therefore it holds true for broad class of problems. And through this approach, we show that the conventional Lyapunov function is an upper bound of the cost function of rollout policy, and recursive feasibility is implied by the sequential improvement condition. In addition, we can see that enlarging the size of S improves the bound, but not necessarily the cost function itself. Our method admits various extensions. One is that if there are some constraints imposed on the entire trajectory, one can use state augmentation to transform the problem back to trajectory unconstrained one. and the method remain valid. Another one is if there are multiple policies and their corresponding sets, a similar method that use policy that is pointwise best applies. The third aspect is that we notice that attaining the minimum of this expression over all control is sufficient to ensure sequential improvement condition, but not necessary. All we need to make sure is that our rollout policy beats base policy in this expression. Therefore, if we replace the control constraint set with some set U bar that contains mu x and optimize over it, we still get sequential improvement condition. And this has application in multi-agent problems where one can optimize first only one control, after which optimize the second control. Thereby, effectively, we construct this set U bar, which is a union of two line segment instead of optimize over the entire ellipsoid. Now let's look at an example that illustrates the structure of the set S. We consider a linear quadratic problem where the control is constrained and the plant is unstable and the cost is quadratic. We introduce a base policy that would bring the state to origin within finite step, and its cost function is piecewise quadratic. And the possible set S could be some discrete points, which can be one run of the system trajectory under the policy, or it could be a continuum range, which would be the conventional MPC terminal constraint, or it could even be a mixture. All we need to make sure is that this forward invariance property holds. And this means we can collect the pieces of cost function and assemble them together, and our method remain valid. To conclude, we highlighted the similarity and connection between rollout and MPC, and we introduced a data-driven variant of exact rollout, and we use fixed point equation for our analysis. The variance admits trajectory constraint, multiple policy, and simplified extensions, and we use a linear quadratic regulation problem to illustrate our ideas, and a few other examples are provided in our paper. And here are some references of our work. With that, I would like to conclude, and thanks for your time.